Today we're going to look at a way of measuring the strength of correlation between two variables. So we're going to be talking about variables that have a linear relationship, and we talked about variables like this last year when we talked about lines of best fit and regression lines. So the variables should be in a relationship that creates a straight line of best fit. So a line of best fit of the form y equals a plus bx. In statistics, we write it in this form rather than in the form y equals mx plus c for no particular reason other than to be confusing. So we've used these lines of best fit, and I think I even showed you how to calculate that equation even though we didn't need to know it last year. And we could see in this line of best fit if there was a positive gradient or a negative gradient. So if we had positive correlation or negative correlation. But we didn't talk about trying to find the strength of correlation. Now, up until A level, you would have been able to look at these graphs and say, we've got strong correlation here, they're all in a lovely straight line, strong correlation, and that is negative correlation because it's going downhill. Or we'd be able to look at something like this and say it's got weak correlation because they're all scattered all over the place, and it's positive correlation. But it would have been tricky for us to compare if we had two graphs where the points were all quite scattered. Would we be able to see which had the best correlation? We'd have to sort of do a bit of guesswork and judge it by eye. Whereas now we're going to look at putting correlation into a number form, so we have a measure of correlation. And one of the ways of doing this is the product moment correlation coefficient, which is a bit of a mouthful, but we normally abbreviate it to Pmcc. And that tells us how the data differs from the data on the line of best fit. And it takes any number from -1 to 1. So if you've got perfect negative correlation, the Pmcc will be -1. So this diagram here will have a Pmcc of -1. And again, to be confusing, Pmcc is called R. So here we have R is -1, and our correlation goes all the way up to +1, which would be perfect positive correlation. So this here, where all the points are on the line of best fit, would have a Pmcc of 1. If we have no correlation, our Pmcc is 0. And then we can take any value between -1 and 1. So if we've got something like this is still fairly strong negative correlation, but not perfect. So we're looking at something like -0.8 here. And over here we've got positive correlation, but fairly weak. So we're probably looking about 0.2 for our Pmcc there. So we would now be able to compare pairs of variables and say which have stronger correlation and which have weaker correlation. I think we've covered everything in these notes here. Now, to calculate that Pmcc, we've got this rather complicated formula, which I'm not even going to read out to you. And that can be written using this notation, which is sum of the squares notation. The Sxy stands for this thing here, the Sxx stands for this thing here, and the Syy stands for this thing here. It can also be written like this, so Sxy is the sum of your difference between every data point and the mean for the x values times by every y value, take away its mean. And then we would add that together for every single set. Now that's really, really complicated, but you are very lucky in that you live in the modern era. Even just a couple of years ago, you would have had to have been able to use that formula, but we can now do it on our calculators. So let's have a look at an example of working out the Pmcc. It's very similar to how we would find a regression line, which I showed you last year, but which you've probably forgotten. So we need to be in statistics mode on our calculator. So that will be option 6. And we're looking at linear relationships. So we're looking at option 2, y equals a plus bx. And then we get a table to complete with our x values and our y values. So if we're looking at this example here where Amelia's buying 4 apples and 3 bananas, then we can type in all of our x values on the left hand side. And we've got 13 of those values, and then we type in our y values on the right hand side, and because we want to know the relationship between them, we need to put them in the correct pairs. So she bought 562 grams worth of apples the week that she bought 366 grams worth of bananas. So we need to line these up. Now it doesn't matter that she bought more apples than she did bananas, because we're not looking at whether the apples were heavier than the bananas or anything like that. We're just looking at whether she bought big bananas in the week that she bought big apples. So we just need to be able to compare which week's data are bigger than other weeks' data. So I've now typed in all of that. Now we can't do anything until we've gone back to the main screen. So if I press AC, and then our regression formula and our product moment correlation coefficient are in option regression calculation, so option 3. And that gives us the equation of our regression line, which we learned how to calculate last year. So we would have a line of best fit with equation y equals 721 minus 0.569x. So we can see we've got a negative gradient. Our product moment correlation coefficient is minus 0.524. Now that is not related, although in this question it is close to the gradient, it's not related to the gradient of the line of best fit. You can have a line of best fit with a very, very small gradient, so a very unsteep line with a Pmcc of 1, and a really, really steep line of best fit with a Pmcc of 1. It's just how close the points in the data lie to that line of best fit that affects your value of R. So if we want to interpret into context our value of R, it's minus 0.5, so it's negative correlation. It's not strong. It's not really weak. We could maybe call it moderate correlation here. So we've got moderate negative correlation. Now it does say in context, so let's think about that, what that means. So that it's negative means that as one value gets bigger, the other value gets smaller. So when Amelia buys heavier apples, she tends to buy lighter bananas. So let's look at Alex's claim now. And Alex says that each week Amelia buys either big apples and big bananas or small apples and small bananas. Comment on Alex's claim. Well, we need to find a polite way of saying it's absolute nonsense, because we've just seen that we've got negative correlation. So let's say there is actually negative correlation. So Alex is wrong. Okay, and then we've got another example here, and this one comes from the large data set. So remember, this large data set can crop up anywhere. And the first question is one to check that you've seen the large data set before. And it says, state the meaning of NA in the table above. And it tells us in the large data set that NA just means the reading is not available. You could probably have guessed that if you haven't seen the large data set. That's not to be confused with when we have TR, which means trace, which we see with things like rainfall, when there's been a smidgen but not enough to measure. Right, now we want to calculate the product moment correlation coefficient. So back to our calculators, still in stats mode, and we need to go into option and select a type of data. So option 2 for linear data. And we need to overwrite those values that we had before with these new values in this table. So 1, 2, oh no. 4, 4, 8, 7, 12, 12, 3 and 10. We're ignoring those two values where we don't have a maximum daily gust, and then just need to delete the extra values that I've got there, and then type in the wind gusts: 13, 12, 19, 23, 33, 37, 10 and 23. So I've now got my 8 values typed in, so cancel, option, regression calculation, and there's my value of R, 0.953. So comment on the suitability of a linear regression model. So are we able to use a straight line of best fit for this data? Well, that's a very positive correlation. So we've got a very strong correlation, so we can use a line of best fit. It doesn't really matter that it's positive, it just matters that it's very strong. Because if we had negative correlation, we'd also use linear regression. Very strong correlation, so a linear regression model is suitable. And that's the end of the examples, so it's your turn to have a practice now.